Hello everyone, welcome back to Linkside 201. Today we are going to talk about set theory. Set theory combined with predicate logic would be a very useful tool to represent semantics. So if we use set theory as meta language, then we can get rid of the circularity problem as in the dictionary. In other words, we can use set theory to define meaning in human languages, so we don't need to use dictionary definition. And this idea will be much clearer in the next lecture. Okay. So, what is a set? A set is a group of stuff. So, for example, if we put all these items inside this box, then this box would be a set. Okay, so a set is just a group of stuff. Okay, notation of set. So this is the easiest way, the most intuitive way to represent a set. We use curly brackets and we list all the members in this set. Okay, so for set A, it's just a bunch of numbers, and B is a bunch of names. Okay. We need to pay attention that normally we use capital letters to represent a set. So set A is this one, set B is this one, curly bracket, and we use comma to separate all the members. Okay. And yet, in addition to enumeration notation, we have two more ways to define sets: description or recursive definition. The above two examples are enumeration, and then we can use description and use recursive definition to define set. Okay, enumeration, we just saw it, and description. So description can be represented in this manner. We use curly brackets as well, and we use a variable. We can use x, y, whatever, and then you have a vertical bar, and then you describe the property of this x. So for example, x is a integer between 1 and 5. So these two are actually identical. They're just notational difference. Okay. And then another way to describe a set is to use recursive definition. So recursive definition, we just need to we define a base case. For example, if we try to define 1 to all the natural numbers, we can use this recursive definition. We define the base case first. 1 is a positive integer, and then if n is a positive integer, then so n plus 1 is also a positive integer. Okay. And then we have this is a recursive case. So we define a new member in terms of an element. They are known members. So we already know n is the member. And then we use this n plus 1. Then we can, n plus 1 will be a new member. And then we have a bounding clause. We say nothing else is a positive integer. So enumeration could be problematic when we have an infinite set. For example, positive integer is it has infinite members, right? So you cannot list all the members. So in this case, we can use recursive definition. Okay, now let's talk about the property of set. First of all, it is not ordered. In other words, a set AB is equivalent to a set of element BA. It's not ordered. And each member in the set is unique. In other words, there's no duplicate member in the set. So this notation would be meaningless. A would be equivalent to these two sets would be equivalent. So it makes no sense to say there are two A's in a set. Okay, and then if we want to know the size of a set, in other words, how many members are in the set, we use vertical bars, two vertical bars. For example, the size of AB is 2. Okay, and there's a special set which is empty set. It's like an empty box. It's just a box and there's no member inside the box. So you can use curly brackets with nothing inside, or just use this notation. So the size of empty set is 0 because no member. However, you can put an empty set inside a set, right? It's like you put an empty box inside a box. So the size of a set containing an empty set will be 1. Okay, and there's another special set which is universal set. We use capital U to represent universal set. Universal set means the set that contains all elements of the universe. It contains everything. Okay, there are some calculation that we can do with sets. The first one is membership. So for example, if we have a set A, 1, 2, 3, 4, 5 are their its member, then we can have a membership relationship. We can say 1 is an element of set A. We use this symbol to represent membership, and is read as is an element of, and we can use this symbol. 6 is not an element of set A. So this operator connects two things, and the result is a truth value. So 1 is an element of set A, 6 is not element of set A, and the result is that this could be true or false. Right? So the result is a truth value. Also, we can have relations between sets. The first relation is subset. We use this symbol to represent subset. So, the definition of subset is that set A is a subset of set Y, set X is a subset of set Y, if every member of X is also a member of Y. So every member in X is also a member of Y, then set X is a subset of Y. So for example, if we have these four sets A, B, C, D, okay. C is an empty set. We have two notations, and D is this one. So we will have this relationship. A is a subset of B because every member 1 and 2 is also a member of set B, right? And set C is also a subset of B because there's no member in C. So actually every member in C is also a member in B. Okay, so subset is empty set is a subset of every set. And D, 6 and 7 is not a member of B. So D is not a subset of B. And also this subset have an identity property. So A is a subset of A because every member in A is also a member of A, right? So it has an identity property. And the related concept is proper subset. So we have subset is this, and proper subset is this. Okay, the idea is very similar. The only difference is that a proper subset excludes the possibility of identity. So if we have the same setting, and then everything will be identical except for A is not a proper subset of A, right? Because proper subset excludes the possibility of identity. However, A is a subset of A. Okay. We can also have other operations between sets. For example, we can have intersection, the intersection between A and B, which means that all the members in A and in B at the same time. Okay, so if we have this setting, we have 1, 2, B, A is 1, 2, and set A is 1, 2, and set B is 1, 2, 3, 4, 5. Then intersection between A and B will be 1, 2. Okay, because only 1, 2 is in A and also in B. And we can have a union as well. It means that elements in A or in B, or in element in A or in D. So if A and D, then the union of these two sets will be 1, 2, 6, 7. Okay. And we can have difference as well. Differences means that elements in B but not elements in A. So if we have, and we use this minus sign to denote the relationship of difference. So B minus A is 3, 4, 5. So we take away elements in A, right? 1, 2. So what is left is 3, 4, 5. And then we can have complement as well. We use a comma to denote complement. The meaning is simply not A. So we have to use a universal set. And so complement means universal set minus A. Okay. So now we have a relative small universal set. We have 1 to 7. And then we minus A would be 1, 2. Then we have 3, 4, 5, 6, 7 left. Okay. Complement means not A. If we have the following operations between sets: union, intersection, difference, complement, then the result will be a set, right? And here's a summary. So we can have two arguments and we have different connectors, so we can do some set calculation over sets. So if we have these connectors, then the result will be a truth value, right? And we have these connectors, intersection, union, difference, then the result will be another set. Okay, and if we have the membership, then the result will be a truth value. This is just a summary. Okay, remember to let's say for today, and remember to do the in-class exercise. Thank you and see you next time. Bye bye.